Okay, let's do derivation to Van Waals gas equation today. So before consider Van Waals gas, let's think about the partition function for ideal gas. So for ideal gas, the partition function is pretty easy, right? It's q equals to lowercase q to the n and divided by n factorial. So, but in ideal gas, the partition function for single particles in a container of volume V is actually this. Lowercase q equals to volume of that container divided by the de Broglie wavelength, which is lambda the cube, and the lambda equals to square root of h square divided by 2 pi mkt. Okay, is the de Broglie wavelength. And okay, let's move to Van Waals gas. In Van Waals gas, each particle can be considered as a hard sphere. So the interaction between the particles, now we have two kind of situation. So the first situation when r smaller than d. So r is the distance between two particles, and d is the diameter of each particles. So when r is smaller than d, that means these two particles are just melt into each other, and at that time the interaction between them become infinity. And the second time when r bigger than d, that means between two particles there's some distance between them. Yeah. So at this time the interaction the interaction can be expressed as negative epsilon times r divided by d. The d divided by r to the 6th. Okay. And in Van Waals gas, the partition function for the whole system is still as same as the partition function for the ideal gas. But this lowercase q is different. Why? Because the V changes. In Van Waals gas, not all volume is available. The particles occupy some volume. So in that case, the new volume becomes V minus n times B. And B is the volume of each particle, of a single particle, which is 4/3 times pi times d divided by 2 to the 3, which is 6 pi over 6 d cube. Yeah. So the lowercase q can be written as v minus mb. Okay, now we entered our Boltzmann factor, which is exponential negative phi divided by 2 kt, and divided by the Broglie wavelength cube. Okay. Yeah. Oh, so why we enter this Boltzmann factor? Because we need to take care of the average intermolecule potential, and we divide potential by 2 is because the interaction energy is shared by two particles. Okay, yeah. So now let's consider some situations in Van Waals gas. For a single particle in Van Waals gas, there are a lot of particles around this particle, right? And we can consider these particles as a shell. Okay, there are a lot of shells around these particles, and other particles are just distributed uniformly around this shell. So now let's consider the interaction energy from a shell to a single particle. Okay, we can do integral in this case. Integral from d to infinity, and we use UR times NV 4 pi R dr. So what is N divided by E times 4 pi R squared dr? So 4 pi, the volume of share is equals to 4 pi R squared times R. I think that makes sense, right? Everybody understand that. And NV N divided by V is basically the density of the gas. The density of the particles, I think, yeah. So we use density of the particle times the volume of the shell. We know how many particles are in that shell. Okay, then the number of particles times the interactions energy between two particles. Then we can get the interaction energy, the total interaction energy from that shell. Okay. Yeah. Then we do integral to this equation. What do we get? We get this. Wait a second. Yeah. Negative epsilon d divided by r to the 6, and v 4 pi r squared dr. Yeah. So integral from d to infinity, and we get d to the 6 divided by r to the 4, and v 4 pi dr. And it's very easy to get the whole equation, which is negative 2a times nv, and a in this term is becoming 2 pi d cube over 3 times epsilon. And you can also do some transformation to this equation. Epsilon times b, times 1 over 4, right? But it doesn't matter. Then we can know the partition function, which is q to the n divided by n factorial, which is v minus mb and the e. Oh, sorry. Yeah, I think that it's 2a_mv divided by 2kt, and the 2 just cancel out, and it's lambda cube 3n and times n factorial, right? Yeah, and then we know the home force free energy is equals to negative kb ln q, and which is equals to negative kt n ln v minus mb plus n square times a times v divided by vkt minus n lambda n lambda cube, and minus ln n factorial. Okay, and from the Lagrange transformation, we know the pressure is equals to negative partial F partial V, and in this case we can get nkt divided by V minus mb minus n squared times a times divided by v squared, and we can rearrange this equation. So now it becomes p minus n squared times a divided by v, and times v minus mb equals to nkt, right? Then we can do some, we can replace n with n equals to n times Na. Then we got the van der Waals gas equation. NB, NRT. Yeah, and I think that's it. That's all. Thank you very much.